All right, let's dive in. You know, at the very heart of every single blockchain, there's this incredible engine. It's a protocol that somehow gets thousands of different computers all over the world to agree on one single version of the truth. And there's no CEO, no central server, no boss in charge. That engine is called a consensus mechanism. And today, we're going to explore the brilliant and frankly super competitive quest to build the perfect one.
But you know, before we even get to computers and code, this is actually a much, much older problem. It's really a problem of trust. So, I want you to imagine something. You're trying to get a big group to agree on one single critical plan. But here's the catch. You know for a fact that some of the people in your group are traitors, and they are actively trying to make the whole thing fail. So how do you do it? How do you make sure the loyal members can still win?
Well, this classic thought experiment has a name. It's called the Byzantine generals problem. Picture this. A bunch of generals have an enemy city surrounded. They all have to agree unanimously to either attack or retreat. If they all attack together, they win. If they get divided, it's a disaster. And the catch, of course, is that some of the generals are traitors, and they're sending different messages to different people to cause chaos. Now this right here, this is the exact challenge a blockchain faces every single second. The generals are the computers on the network. The traitors are hackers or malicious actors. And every single consensus mechanism is, at its core, a solution to this very problem.
Okay, so as we start exploring these solutions, we have to understand the rules of the game. And that brings us to the famous blockchain trilemma. The idea is that it's incredibly, almost impossibly difficult to build a network that is great at all three of these things at the same time, being decentralized, being secure, and being super fast and scalable. You can usually nail two of them, but you almost always have to make a big sacrifice on the third. And it's this constant tension, this trade-off, that has been the engine driving all of the innovation we're about to talk about. So here's our game plan for this explainer. We've covered the basic problem. Now we'll look at the very first solution, proof of work. Then we'll jump to its biggest rival, proof of stake. After that, we'll get into some wild new ideas, the modular future. And finally, we'll see how they all stack up in the great balancing act.
Our first stop is proof of work. This was the OG solution, the brute force breakthrough that Satoshi Nakamoto baked into Bitcoin back in 2009. And it was really the first time anyone had come up with a working, practical solution to the Byzantine generals problem in a totally open, permissionless network.
So, how does it actually work? Well, think of it like a massive global lottery where miners all over the world are racing to solve a really, really hard math puzzle. The first one to solve it gets to add the next block of transactions to the ledger and gets a reward for their trouble. What this does is it turns security into pure, raw economics. To attack the network, you'd need so much computer hardware and so much electricity that it would be astronomically expensive. So instead of trust, the system is built on verifiable cost. It's basically voting with computer power.
And this system is the perfect example of that trilemma we just talked about. I mean, look at this. Proof of work is an absolute beast when it comes to security and decentralization. It's battle-tested. But the trade-off? Scalability. It's just slow. It can only handle a handful of transactions per second. And that slowness is a direct result of that incredibly difficult, energy-guzzling competition that's needed to keep it so secure.
And yeah, that huge energy cost became proof of work's biggest Achilles heel. I mean, we're talking about networks like Bitcoin using more electricity than entire countries. This, naturally, drove a huge search for a better way. And to give you some perspective, when Ethereum, the number 2 blockchain, finally made the switch away from proof of work, its energy usage dropped by over 99%. That's not a typo. The savings were just staggering.
So this brings us to the next big leap in this evolutionary story. People started asking a really smart question. Instead of securing the network by burning massive amounts of energy, what if you could secure it with capital, with money itself? And that is the fundamental idea behind proof of stake.
This was a completely different philosophy. See, proof of work relies on external resources. You have to go out and buy hardware and pay for electricity. Proof of stake, on the other hand, uses internal resources. Validators lock up their own crypto coins as collateral, as skin in the game. And if they try to cheat the system, the network automatically destroys or slashes their deposit. So security is no longer based on physical cost. It's based on direct economic risk.
And just like real-world political systems, proof of stake started to evolve. You have the basic version, which is kind of like a direct democracy.
The more coins you stake, the more influence you have. But to get more speed and efficiency, developers created delegated proof of stake, or depots. This is more like a representative democracy. All the coin holders vote for a small, select group of delegates, and those delegates are the ones who actually run the network. This makes things way faster, but, as you can probably guess, it starts to concentrate power, creating centralization risks. Now, at the same time this whole work for stakes debate was happening, another family of consensus mechanisms was being perfected, coming from the world of classical computer science. These are called BFT-style protocols. And here, validators engage in a very explicit, multi-round voting process to approve every single block. The results are speed, and maybe most importantly, something called deterministic finality. It's a fancy term, but it just means once a block is confirmed, it is final, forever. There's no chance of it being reversed.
Okay, now we're getting to the really fun stuff, the cutting edge. After struggling with the trilemma for years, some innovators started to challenge the most fundamental assumption of all. They asked, what if a blockchain doesn't have to be a chain?
And this thinking led to some pretty radical new architectures. First, you have things called directed acyclic graphs, or DAGs. In systems like IOTA or Nano, there are no blocks, no miners. Instead, each new transaction just confirms a couple of previous ones, creating this interwoven web, or tangle. This lets tons of transactions get processed in parallel. And then you have Avalanche, which uses a completely different, almost gossipy protocol. Instead of everyone voting at once, nodes just ask small, random groups of other nodes for their opinion, and they repeat this process over and over at lightning speed until consensus just emerges. It's a wild idea that allows for thousands of validators to participate.
This all brings us to today, and to what is probably the most profound trend in the whole space, modularity. The core idea here is, maybe the trilemma is a trap. Maybe the goal isn't to build one single, perfect blockchain that can do everything. Maybe the answer is to stop trying, and instead build a system of specialized, interconnected layers. This modular approach is all about unbundling the blockchain's job. A traditional or monolithic chain tries to do everything itself. It handles the transactions, it secures the network, and it stores all the data. And that makes it really secure, but also really slow and expensive. Modularity says, let's break those jobs up. Let's have super fast and cheap Layer 2 rollups handle all the busy work of executing transactions, and then they just post a simple summary of their work down to the main Layer 1, whose only job is to be the ultimate source of security and final settlement. So, wow. After that whole tour of innovation from brute force all the way to these complex modular systems, let's just take a breath and see how all these different approaches actually compare in that great balancing act. This little cheat sheet really puts it all together. You can see those trade-offs in black and white. You've got proof of work up top, the king of security but super slow. Then proof of stake, which is a nice middle ground, getting you efficiency but maybe losing a bit of decentralization. Depots pushes that even further, sacrificing decentralization for raw, blazing speed. Then you have Avalanche, achieving huge scale and high decentralization, but its finality is probabilistic, not absolute. And finally, rollups, giving you incredible speed by basically borrowing security from another chain, but adding a new layer of complexity to the whole system.
You know, if you take just one thing away from all of this, let it be this quote right here. After this entire incredible journey of innovation, the conclusion is crystal clear. There is no single best consensus mechanism. There's no one-size-fits-all answer. The needs of a global digital currency are completely different from the needs of a private supply chain network. The best choice is just the one that makes the right trade-offs for its specific context.
And that leaves us with one final, really big question to chew on. Is the ultimate goal of all this work to finally discover that one single perfect chain that will rule them all? Or are we actually building something that looks a lot more like the internet itself? A diverse, vibrant, interconnected ecosystem of many different blockchains, all specialized for different things, but all able to talk to each other. The way things are trending with modularity, it really seems like we're headed for that second option. The quest for the perfect ledger? Well, it's not over. It's just getting a whole lot more interesting.